Hello, everyone. This is Group 1 presenting digital transmission in free space through a high-powered laser. Our mentors being Dr. Wei and Dr. Carr, our committee being Dr. Sahawin and Dr. Maddox and Dr. Eikenberry. Meet our team. Alexander Simmons, a photonics engineer. Curtis Kane, an electrical engineer. Ivan Huang, a photonics engineer. And Monica Castro-Suarez, a computer engineer.
My name is Ivan, and the basis of our project is on long distance communications, which was forever changed thanks to the invention of the electric telegraph in the 19th century and the laser and fiber optic cable in the 20th century. And as we're transmitting digital signals, which are composed of ones and zeros, a laser can be modulated to transmit these signals as a series of on and off pulses. And currently, free space laser communications exist, but mostly in satellites. As for our motivation, the project will involve transmitting digital data over free space with an infrared laser. Um, The laser will transmit a series of pulses which a photodiode on the receiving end can detect and then generate current. That current will be amplified with a transimpedance amplifier or a TIA and decoded with an MCU or microcontroller unit. The project will aim to demonstrate the possibility of terrestrial free space laser communications where rapid transmission of sensitive data is critical. As for our goals and objectives, for the laser diode transmitter, we would want to design a modulator circuit to convert digital data into pulses for the laser and to achieve a bit transfer rate of at least 20 to 30 kilobits per second. For our optical system, we would first want to find a focusing lens with a 99% transmittance at 980 nanometers, which is the wavelength of our laser, um, with a large diameter and a small focal length. Test different lens configurations for the expanding lens portion, and to ultimately design a compact system with as few lenses as possible. Lastly, for our photodiode receiver, we would want to ensure that it can generate the max amount of current when exposed to the laser, and to ensure that the decoding algorithm can read the signals at the rate at which the laser is transmitting. For our stretch goals, we would like to introduce encryption and error correction to maintain the quality of the signal. Um, Further develop the system to allow for bidirectional capability. Increase the bit transfer rate to the megabit range so that we can transmit more and more data. Expand the system to include the modulation and transmission of voice signals, and then to scale the system up for potential off-grid or emergency use.
Hello, my name is Alexander Simmons, and I will be going over the optical component selections and all the comparisons through there. This first page is essentially a brief overview of the optical parts used in the project, what they're used for, along with a brief justification of why we chose them, and we will go more into detail with that in the next few slides. Uh, First, we have the laser diode, 980 nanometer, beam expander at the transmitter end, which is a positive meniscus lens, a focusing lens on the receiver end, which is an aspheric lens with a numerical aperture of 0.55, a photodiode, which is a silicone pin photodiode at 0.6 amps per watt at 980 nanometers, and we have the optical filter, which is a bandpass filter at 980 plus or minus 10 nanometers, with the OD of greater than 4. Onto the component comparison table of the laser diode. that we used, such as TTL modulated laser diode, pulsed LED, femtosecond fiber laser, to name a few. The reason why we went with the TTL modulated laser diode is because of its simplicity, affordability, and adequate modulation speeds for free space optical communication. Compatibility with beam shaping optics at 980, and that higher end lasers like the femtosecond or the TI Sapphire were ruled out due to excessive costs and complexity not needed for mid range data links and communication. The photodiode itself, uh, we selected it due to its high responsivity, the support of pulse modulation, its low dark current and noise, its adequate speed for TTL modulated laser pulses, which is transistor logic, and its effective free space optical range up to 2 kilometers with optical focusing. We avoided the avalanche photodiodes because of their unnecessary complexity and cost. For our beam expander component, we chose the positive meniscus lens because it had a lower divergence compared to other lenses. It had a happy moderation of in its spherical aberration correction. It had a high transmission, a compact design, and less complexity and cost than its counterpart, the achromatic doublet, and had a more compact footprint compared to it as well. For our focusing lens, we went with the aspheric lens because of its numerical aperture and how it enables strong convergence from wide input beams, its low aberration or wavefront errors, which improved our accuracy, focus of the expanded beam tightly onto the photodiode, and maintaining a high throughput with AR coated coating, which was optimized for 980 nanometers. For our optical filter, we went with a bandpass filter at 980 nanometers because it essentially blocks out unwanted ambient light with its OD of greater than or equal to 4 across visible and infrared light. And it also enhances our signal to noise ratio under outdoor lighting conditions. And it is more effective in that way than the short pass or long pass alternatives. This is our optical system diagram. It's essentially just the layout of the system, beginning with a microcontroller that modulates the 980 nanometer laser diode using TTL signals, then goes to a beam expander off of a mirror using the meniscus lens as we saw in the last few comparison tables. We use that to reduce the divergence and maintain collimation over long distances. After traveling through free space for about a kilometer, the beam then passes through a 980 nanometer bandpass filter, blocking out ambient light, and then into a focusing lens, which concentrates the beam onto a photodiode, which then converts the optical signal back into electrical signal for decoding and display. Ooh. The atmospheric effects on free space optics, essentially the main takeaway is that a smaller beam waist leads to a greater divergence, and beam spread over distance is reducing the intensity at the receiver. Consequences that appear over long range, 1 to 2 kilometers, low receiver power with a spot mismatch, more sensitive alignment, and reduced SNR. This is just a visual example of atmospheric turbulence, how it affects a narrower beam. The design solution that we ended up going with for using the beam expander and the focusing lens, we used the beam expander to expand the beam from 3 to 5 times its original size, which reduces the beam wander and ensures necessary optical power is captured by the receiver. And the focusing lens at the receiver end reconverges the expanded beam into the active area of the photodiode, which maximizes the photon current conversion via concentration of the light. All right. The speckle and beam pattern is one of the main things that pop up when you expand a beam to the size of 2 to 4 inches instead of 1 to 2 millimeters. And the main takeaway is that as a smaller beam, speckle pattern is dense, but in a larger beam, the speckle pattern or speckle grain is more visible and difficult to average. The effects of the solution from effects of expanding the beam is that it improves our SNR, reduces alignment sensitivity, and improves detection reliability. Next slide is just a visual example of the speckle pattern on the right in number B. You can see the hot spots in the beam right there. All right, on to our system testing. This is essentially just our main optical calculations we are concerned with, mostly being atmospheric attenuation, atmospheric turbulence, and beam spread. The main softwares we used for testing and modeling were Zmax and MATLAB, which we will go into and explain later on in this presentation.
Hello, everyone. My name is Monica. For software comparison, I am using the MSP430G553 for testing and to implement onto our microcontroller when we build our PCB. I tried 3 different softwares, which being Code Composer, Arduino IDE, and MicroPython, and chose Arduino IDE due to I am able to use C language as well as it is user-friendly. Though its performance is medium compared to Code Composer, it still works well with me and what I needed to do.
Hello, this is Curtis Kane, and this is the start of the hardware design. This slide shows an overview of our hardware pipeline. It starts with a microcontroller that converts written text from the laptop to binary data that will be used to toggle the laser in a subsequent manner so that zeros will represent when it is off and ones will represent when it is on. The laser beam then travels through an optical path composed of lenses and mirrors for beam shaping and collimation. At the receiving end, a photodiode captures the signal and the output current is converted to voltage using a transimpedance amplifier. Using the microcontroller's built-in analog-to-digital converter, the signal is then processed by the microcontroller and its output is then sent to the LCD to be displayed. We chose the ATmega 328P as our microcontroller for our main PCB because it has a robust community, wide Arduino compatibility, and sufficient specs for our task. It features 32 kilobytes of flash and 2 kilobytes of RAM, allowing us to buffer and process binary signals fast and effectively. Its 10-bit ADC is perfectly adequate for reading the photodiode amplifier output and transferring it to our LCD display. Most importantly, its 1.8 to 5.5 volt operating range gave us flexibility with the voltage regulation. This schematic shows how we wired the ATmega 328P to support laser modulation, photodiode input, and LCD output. The inclusion of programming headers to reprogram the MCU aids in making the PCB easier to troubleshoot in the future, as we can now adjust the code on the fly if any parameters were to be changed. Power connections to both 5 volt and 3.3 volt rails are also included as part of the MCU design to power both the LCD header and the MCU itself. This clean layout will allow us to easily troubleshoot and test each stage of the system. The OPA 381 was our amplifier of choice for the photodiode to transimpedance amplifier signal chain. Since it is optimized for transimpedance applications, it has a very low input bias current of only 3 picoamps on average. Its 18 MHz gain bandwidth makes it ideal for detecting fast optical pulses with minimal signal degradation. And at around $1.80 per unit, it offers strong performance without breaking the budget. Here you can see our transimpedance amplifier circuit using the OPA 381. Instead of a single hardwired photodiode, we opted for a header to bring more adaptability to our overall circuit design. This header will allow us to swap the photodiode easily in direct response to any dramatic changes in wavelength of our input laser. With the photodiode wired into the header, the photodiode's current will enter an inverting input, and the output will provide a clean voltage signal proportional to the light intensity. To power the system reliably, we implemented two boost regulators on daughter boards. We used the TPS 613221A to generate 3.3 volts for the amplifier, and the TPS 613222A for 5 volts to power the microcontroller and LCD. These regulators helped ensure stable performance even as battery voltage dropped, which is critical during long testing sessions. This slide brings it all together, showing the complete system schematic. You can see the flow of signals from the photodiode and amplifier into the microcontroller, which then sends data to the LCD. It also shows programming pins and extra LEDs for debugging, an important feature that will save us time during development.
This is the software design. This system enables wireless data transmission using a high-powered laser. Input data is encoded into binary by microcontroller and sent as light pulses via optical transmitter. A photodiode receiver captures the signal and converts it back into electrical data. A decoder reconstructs the original message, which is then displayed on a LCD. The software manages encoding, timing, error handling, and display formatting for reliable real-time communication. And this is the general overview of the software design, which is the input, which then goes into the microcontroller, which encodes the binary into binary conversion, which then goes into the switch, and then goes into the high power laser, then the optical transmission system, then the open air transmission, then the optical receiving system, which then goes into the photodiode detector, which then is received by the PCB and then is decoded, which then is displayed by the LCD screen.
As we began testing, we encountered two major issues. First, our initial microcontroller, the MSP430, was not giving stable results. Switching to the AT Mega 328 solved this brief problem and even simplified our code. Second, we initially overestimated the photodiode's output current, which led to overamplification and invalid readings. This was swiftly fixed by retesting components and recalculating our results. These issues helped us better understand the importance of theoretical verification and proper component matching. Our current setup is now functioning with accurate readings and stable digital output.
Prototype and testing, the software section. In this demo, I tested the LCD and LED control logic before the final hardware was available. I used the MSP430 FR6989. Due to its built-in LCD low power use and compatibility with Code Composer Studios. The system's initialized GPIO and LCD settings displays the numbers 430 using the 7-segment lookup and controls the red LED on P1.0. In future versions, will allow users to input words like hello world, showing each character on the LCD along with its binary form. While the LED blinks on and off based on each binary bit, this serves as a proof of concept for display and I/O logic ahead of for a full system integration in Senior Design 2. Problems encountered and solutions developed. One of the initial challenges during the preliminary testing was selecting the appropriate MSP430 development board. The decision was between the MSP430 FR6989 and the MSP430 G553. The MSP430 FR6989 was chosen for prototyping due to its integrated LCD module, which is which enables the convenient testing and visualization of the output without the need of an external component. However, the final implementation will transition to the MSP430G2553, aligning with the microcontroller used on the custom PCB. The developed code will be ported accordingly to ensure compatibility with the targeted hardware.
The photodiode that we will be using is an FDS 100 silicon photodiode from Thor Labs. The critical measurement of the photodiode that we will be taking is the responsivity, as it will determine the amount of current generated per watt at the given wavelength. From Thor Labs specification sheet, the theoretical responsivity is 0.6 amps per watt at 980 nanometers. Since we are still waiting for the laser diode to arrive, we have yet to measure its actual responsivity. And for our optical system, we used Zmax to model it. On the left is a 3D diagram of the optical system with the theoretical path length. And on the right is a table of parameters of our system. The parameters were optimized so that Zmax can model the most efficient optical system. For our bit error rates, we used MATLAB to generate this plot. And this plot is a simulation that shows the bit error rate with NRZ modulation or non-return to zero at different bit transfer rates. The plot was simulated with code generated by Google's Gemini. And the plot shows that as the bit transfer rate increases, the bit error rate decreases as the signal to noise ratio increases. Although this is a theoretical plot, it shows that transmitting at higher rates is desirable to limit the amount of errors in transmission. Once we have all of the equipment and begin working on the project, we will measure the actual bit error rate with an oscilloscope. For communications, we use Discord and Microsoft Teams. Discord is a free software that allows the creation of text channels to separate conversations by topic and allow for voice calls for remote meetings. And it's readily available as we already have accounts, and it is easy to use. And we also use Microsoft Teams to collaborate on documents, especially Word documents. And it operates in real time, so version control is not an issue. And as for work distribution, Curtis is doing PCB design and 3D modeling. Alexander will be doing optical design and laser calibration and alignment. Monica will be doing website design and management and embedded coding and software design. And I will do optoelectronics testing, modeling and simulation of the optical system, and testing and aligning the lenses and mirrors. Onto our budgeting list is a color to organize the components into optical components in red, computer-oriented electronic components in blue, and analog electronic components in green. The prices, quantity, extra details, and seller links are listed, although some spaces are empty or marked as TBD, as they are still pending for review and purchase. And the list shown below is the first portion of the optical components list. This is the second list of optical components. This is the list for the computer-oriented electronic components. And lastly, this is the the list of the analog electronic components.
Progress and plan for completion. To build a strong team dynamic and set the project up for success, several key meetings and events were held early on. These meetings focused on discussing project goals, aligning expectations, and laying out a clear direction. This helped provide a solid foundation for work ahead and ensured everyone was on the same page from the start. Progress chart for senior design 2. So we have the PCB schematic, which we are almost completed, as well as the optical design. We are almost completed and still in progress, almost there, as well as the embedded software, and the prototype construction, as well as the prototype testing, as well as the calculation. All of this is to ensure that we are done with this project by the end of the semester and it is working by the time we present. This is the plan for completion. This will ensure that by the time we get to the final project review submission or the showcase, we are ensuring that everything is submitted on time and for our team to know when the due dates and when to submit things on time as well. Does anyone have any questions, any concerns, or anything you would like to know about our project? Please let us know. Thank you.